Reliability is a degree to which the results of a measurement, calculation, or design can be depended on to be accurate. As engineers, we must know the reliability of our products. And to do so, we have to conduct a great many number of experiments in order to evaluate the properties and performance of our designs. One example we can look at is in just say running shoes. If we were to design a new world-class running shoe, we would need to manufacture many of those prototype shoes, and then we'd need to test their abilities to undergo wear and to survive out to a certain number of cycles or steps to failure, right? And we'd want to know the reliability of our shoe to know if it is world-class performing, if it's the best shoe on the market, or if it is a poor design that we need to then go back and reiterate and innovate on and improve. Another example is in 3D printed materials. In 3D printing, there's a lot of issues of orientation dependence if you print a part straight up versus on its side or at different angles. But also if you print a part on one side of the build plate or another side of the build plate, there can be a lot of variation in the properties of those within the build space. And from plate to plate, one plate, another plate, a third plate, a fourth plate, from each build, you can get a lot of uncertainty. And so we need to run many tests in order to assess the reliability of 3D printed materials. Now, once we've collected a lot of data, we've got all of these tests, we then want to find what is the probability of failure, which represents the likelihood that a product will fail under a specific condition. So what we do is we get that great many number of experiments and we plot them as a probability distribution function. Now here is an example of two functions, one that has a very high peak, so it has a very tight grouping, one that has a more wide distribution. Here what we're going to say the x-axis is the ultimate tensile strength. So we're going to say it's the ultimate tensile strength of those 3D printed bars. And we run many, many experiments. And for each value of UTS, say there are 10 samples that have a UTS in this range. And there are 5 samples that have a UTS in this range. And say there is 1 sample that has a UTS there. So the frequency, the number of samples with a similar value of UTS. If we continue to plot that data, and sometimes there may be outliers or underliers, we end up with what we call a probability distribution function. Now, these distributions can take many different shapes. They don't always have to have this nice bell shape, but the typical distribution does have this bell shape, and we call it a Gaussian or normal distribution in terms of where the average value is, the most average value, the most frequent value, versus the standard deviation or values that are one standard deviation out. So we take our data, the bar graphs, the actual values, and we transform it into an equation, this Gaussian normal distribution, right? Now this function f of x, where x is our property, say UTS, is equal to 1 over sigma x bar, which is a standard deviation, times the square root of 2 times x, times the exponential, all in brackets, of negative 1/2, in brackets, x, which is our value of UTS, minus mu x, which is the mean value of our distribution, divided by sigma x bar, standard deviation, in a bracket, squared, in a bracket, closing our exponential. And then this function is going to give us that smooth equation that represents our data, our actual frequent data, the number of samples that we have under each value of UTS that we find, right? Now, another important parameter that we can define is the Z parameter. The Z parameter represents the number of standard deviations that the specific value is away from the mean. So if we have a specific value, say we want to say the UTS ranges from 0 to 100, and we want to know how many number of standard deviations above 75, then we'll put 75, UTS is our value, minus the mean divided by the standard deviation, which gives us our Z parameter, right? Now note that the Z parameter, we say Z sub alpha. Alpha is something that we can find, the alpha value, by inputting the Z that we've calculated into a statistical table in our textbooks, table A10 of the textbook appendix. And then that will then allow us to find an alpha value. So let's look at this table from our appendix, table A10. We can see that Z is here. We can see that the first significant digit, 0.0, 0.1, 0.2, and the second significant digit, 0.00, 0.001 are here. So what we can do is put those together. So say Z alpha, we've calculated it using this equation to be 0.36. Then we'll find the 0.3, we'll go over to 0.6, and now we've found the alpha value. The alpha value for that Z is equal to 0.3594, right? Now this is going to be important because this alpha value then allows us to find what the probability of failure is for our product. So finally, with alpha in hand, the probability of failure can be obtained, where the probability of failure, P sub F, is equal to either of two choices. It's either equal to alpha directly when the Z value is less than or equal to 0, so we've got a negative 0.36, or it's equal to 1 minus alpha when the Z value is greater than 0, meaning it's equal to 0.36. And this distinction basically tells us, is the Z to the right of the mean, of the average value, or is the Z to the left? Where are we on that distribution map, right? So let's do an example. Let's do an example of reading this map and figuring out what the probability of failure is for a problem. So in this example, we have 3D printed polyoxymethylene or POM filament. It's the same type of one of the filaments you can print on a MakerBot or a Bamboo Labs, right? And we're testing that filament in a laboratory to failure. So we're pulling it apart and finding its failure load. Now we perform many tests and we find the mean and the standard deviation of the failure load is 1.1 kilonewtons or 0.25 kilonewtons respectively. We are going to assume that this data has a normal distribution, that nice little bell shape. And we're asked, what is the probability of failure for a specific load of 1.01 kilonewtons? So if we wanted to specify what is the probability of failure at 1.01 kilonewtons, if load was there, how many of our samples would have failed or have failed, right? So let's go ahead and think about this. Our knowns are the failure load, the value of its mean and standard deviation, and our unknown is the probability of failure, which requires us to find the alpha value, which requires us to find the Z parameter. So let's start with that Z parameter, where Z is equal to the specific value of interest, 1.01, minus the mean divided by the standard deviation. We put in our knowns of 1.01 minus 1.1 divided by 0.25, and we find a Z parameter equal to negative 0.36. Our Z parameter is negative, right? We've got a negative Z parameter. If our Z parameter is less than or equal to 0, then our probability of failure is equal to alpha. Well, we already discussed that 0.36 gives us an alpha value of 0.3594. And so our probability of failure is equal to 0.3594 or 35.94%. So if we specify a load of 1.01 kilonewtons, then 35.94% of our samples would have failed at or below that load. Now, another important thing for us to look at is discrete data. Events typically arise as a discrete distribution, which can be approximated by a continuous distribution. Now, what that means is we can often find a UTS that repeats many times up to a certain number, and then another UTS that repeats many times and up to a certain number of events. Each of those has its own mean, each of it has its own frequency or count, and how do we then aggregate those individual distributions in order to get a continuous distribution? So let's start with just defining discrete mean and discrete standard deviation. The discrete mean, x bar, is equal to 1 over the number of events summed. So we're summing from an integer of 1 up to k, which is a total number of samples, times the frequency f sub I times x I, which is the value of that frequency. The discrete standard deviation, S of x, can be found as the sum of the square root, it can be found as the square root of the sum from index I equal to 1 to k of the frequency of that specific value times the specific value squared minus the total number of events times the mean squared divided by the number of events minus 1. With these discrete and mean and standard deviation, we can then plot a normal distribution for these kind of discrete distributed data, and then do the same thing, find a z parameter and figure out the probability of failure for groups, many different groups of distributions. Now, finally, let's talk about reliability. Reliability, the R, can be expressed as R being equal to 1 minus the probability of failure. It's basically the opposite of probability of failure. It's like, how reliable is our design? If the probability of failure is 30%, then our design is 70% reliable, right? Now, mechanical systems have many components. And when any one component fails, the system can be said to be a series, and so the system can be said as failed. So the reliability of components in a system, we call that Ri, and N being the number of components. So the reliability of a system with many different parts that have different reliabilities, that reliability capital R, or you could say bold R, is equal to the sum of the reliability of each individual component, right? So let's consider an example. Let's consider we've got a shaft. There are 2 bearings, 2 components, and they each have different reliabilities, one of 95% and one of 98%. And our goal is to determine the overall reliability of the shaft system. Well, then we're simply going to sum the reliability of the first shaft and the second together, and we find that their aggregate reliability is less than their individual reliability. It's equal to 0.93, which is 93%. What this also tells us is that as we add more and more components, where reliability is typically less than 1 in real systems, real designs, the reliability of our system decreases. So the more complex a design is, the larger our value of N is, the greater, the bigger it becomes, the less reliable our design. And what this means is when we're designing things, we want to minimize the number of components and the complexity to increase its reliability.